Hello and welcome to this short introduction video to our recent preprint on the time periodic behavior in 1- and 2-dimensional interacting particle systems. This project was mainly motivated by the following question. So if you take some Markov process with semigroup S and some initial distribution mu, and then consider limits along subsequences as the time tends to infinity, are then all of these limits, if they exist, actually stationary measures for your Markov process? This question is probably best understood in a setting of continuous time Markov chains on finite state spaces. There, the definite answer is yes, at least as long as your generator is irreducible. This is due to the fact that in this situation, no matter in which initial distribution you start, you always converge to the unique time stationary measure. Another situation where this question is well understood is the one of finite range interacting particle systems in one spatial dimension. There, a result by Mountford from the 90s shows that here also every limit point is actually a stationary measure for your process. But roughly 10 years ago, Janle and Külske constructed an example of an interacting particle system in dimension at least 3, where this is not the case due to the existence of time periodic orbits. However, these two last results still leave a big gap, because on the one hand, Mountford only covers finite range systems in one dimension, and the construction of Janle and Külske only works in dimension at least 3. So we were interested in what can happen for long-range systems in one dimension and two-dimensional systems in general. Of course, we were not just interested in any interacting particle system, but only in interacting particle systems that are in some sense non-degenerate. By non-degenerate, we mean the following. We mean that for any finite volume delta and any two configurations eta and xi that agree outside of delta, there should exist a sequence of finitely many jumps such that we can go from eta to delta, and all of these jumps can actually happen with strictly positive rate. This condition implies that for all times t larger or equal than 0 and all local events a and b, the transition probability of ending up in b if we started in a is strictly larger than 0. So under this non-degeneracy condition, our systems are actually behaving truly random, and we can completely exclude all trivial examples. Our main result is now as follows. We showed that there exists a non-degenerate interacting particle system with a finite local state space and translation invariant rates such that it on the one hand admits a unique translation invariant time stationary measure, and additionally there exists a family nu-t of non-stationary measures that actually lie on a time periodic orbit for our dynamics. This shows, on the one hand, that even in 1 and 2 dimensions, one can have macroscopic synchronization. So if one looks at the cosine of the spin at the origin at time t, this oscillates as time t varies. And moreover, one can also interpret this as the birth of a limit cycle or Hopf bifurcation. So if one has weak interactions, one only has this unique translation invariant time stationary measure and no periodic orbit. But as the interactions get strong enough, suddenly this periodic cycle is born. Now let us briefly talk about the construction idea. As an input, we take a continuous spin system with local state space, the unit sphere, and we want that this continuous spin system has a phase transition, so that actually we can parameterize its extremal Gibbs measures by the angle. Now we can just rotate these extremal Gibbs measures deterministically. Of course, this is still very degenerate and not stochastic. So what we do next is we actually discretize the unit sphere into Q discrete arcs. Now, if this discretization is fine enough, so Q large enough, we actually have a bijection between this set of extremal Gibbs measures of our old specification gamma in the continuum and the extremal Gibbs measures with respect to a new specification gamma prime in the discrete world. So in particular, we have this family mu t prime, which is again indexed by the angle t, which we can interpret as a rotated version of these discretized extremal Gibbs measures. Now, the main difficulty is to show that actually these discretized rotated Gibbs measures can be interpreted as a measure value trajectory of some suitably chosen interacting particle system. In the original construction by Janle and Külske, this is done by a Taylor expansion argument. But this Taylor expansion cannot be used for our systems due to the long-range interactions, which introduce some regularity problems in the original proof. So we had to come up with a new idea to actually identify these two trajectories. And here, the main idea is actually to use the fundamental theorem of calculus and say that if we integrate this rotated extremal Gibbs measure against some observable f, or we propagate our Gibbs measure with a semigroup, can actually write this difference as an integral over this time derivative. And now it suffices to show that this time derivative actually vanishes. Now, if we look at this function, what happens in here is that we actually rotate forward in time, but apply our semigroup backwards in time. So intuitively, what one needs to show is that these two rotations actually cancel out. For the technical implementation of all of this, you can have a look at our preprint, and if you have any comments or questions, then feel free to just write us an email. And with that, I'd like to thank you very much for your attention and wish you a lot of fun reading our article.